let's say, a stress testing tool for some protocols, and that was kind of the origin of this talk and of a research project whose goal was to implement some easy-to-use tool or framework for fuzzing on layer 2. So this is the agenda. We are going to characterize the fuzzing framework situation out there before the work we did. We are going to tell you why we initially chose Spike. You might have noticed that we added something here since we filed the submission for the CFP, which was accepted in the first round, so in December. Since then, world has moved a bit, and we decided to port our work to Saleh. We will explain later why. So, why we chose Spike, why we chose Saleh later, limitations and additional features we had to implement, and the more interesting part than that kind of theory might be which protocols have reported to that frameworks, and some results from the initial testings we did. Just to give you an idea what fuzzing is about, I mean, there's a lot of hype around fuzzing since 12 to 24 months. For those of you who are not aware of what fuzzing does, here are two definitions. I won't read them. You can do it your own. The most basic things are, it's about an automated process, and it's about using malformed or in some way invalid data to find out how some entity behaves when it is confronted with that kind of data. So far, there was no, at least to our knowledge, no layer 2 fuzzing stuff in the free tool space. There are some options in the commercial space which are used in vendor labs and in carrier space, which is where I mainly work. I'll get back to that later on. These are the options. So one of them, I think Mu is a sponsor here, so they will be delighted to be on the slide. But maybe they are not too delighted that we have implemented some stuff in the GPL covered space. But that's what we did is not competing with these kind of solutions. There are some tools out there in layer 2 space as for packet crafting. The most prominent example is Yersinia, which was released at Black Hat 2005 in Europe. Yersinia is a good tool, but obviously the main goal is to build conforming network packets, not to build packets that violate boundaries or that violate specifications. So a different scope than what we did. So why did we jump into this space, or why did we feel a need to do something here? It's easy. As I said, we are at least my person, I'm working mainly in carrier space, and there are situations, most of you will know that situations, you think, oh, it would be handy to have a tool now for this or that purpose, and you try to Google or look up SourceForge or whatever, and you don't find anything. We wanted to fill the slot kind of, and given that ENW, there's a lot of research within ENW. It's one of our main, let's say, main foundations. We wanted to build up some knowledge about fuzzing, how fuzzing works, what's out there, and to build up some knowledge about protocols, which is the main reason that so far we mainly have implemented a bit exotic protocols. Some of you might not even know those protocols you'll find in this talk, but I mean that's not bad, so you get knowledge of them. And it was meant to get, for us to get an impression how stable some devices perform. It was not, sorry for that guys, it was not explicitly for vulnerability research. What we have done, obviously you could use it for that, but for us, defining the protocols and observing network behavior was more important than looking for exact parser weaknesses once we encounter problems. But again, some of you might use that stuff for this purpose. For us, it was not the main driver of this research project. What's been out there? Kind of before. I mean, it's the same space now. Just we added something. Those are from our perspective, we did some research, what's out there and what can be used for which purpose. These are the options which could be mainly found. That's Spike and Sully, which we'll cover within this talk. There's something called AutoDafe, there's Peach and TPF. Most of them are not, let's say, too well maintained. That applies in some sense to Spike as well, but so even if there is something, that doesn't mean you can really use it for your purposes or your it does what it tells to do. So from those options, we initially chose Spike as it kind of includes proven fuzzing strings. I mean, Dave Vitale has most probably most of the discoveries most of the vulnerabilities he discovered in, let's say, 2003 to 2005 have been discovered with some aid of Spike. So the stuff which is in there might be useful, might be kind of tested. It will show up that the fuzzing strings are mainly intended, those which are there for kind of Windows environments. But they still work with network devices, as we'll see. Which gained some sympathy from our side was the fact that Spike, the older version, was written in C. You could use it quite efficiently, and I mean, it was under GPL. So good, it fulfilled our requirements, and we jumped in about 1 year ago using Spike. Again, this has changed in the meantime, but I will cover this later on. Running Spike is quite easy. Get it, unpack, configure, make. Once you have done that, you have a set of functions, and you have a set of programs which you can use from command line. So you can kind of run it on command line, or you can use the functions to build something above that. That's exactly what we did. This is how a Spike sample script looks like. There are those are protocol definitions. I won't dig into too much detail in this stuff. We will cover this later. Just to give you an idea, this is a Spike kind of definition, SPK script for NetBIOS. And here are the parts that are fuzzed within a process then later on. There are some static fields, and there are some fields which are filled with fuzz input. And all this together is put into a packet which is sent over to some destination. Okay, I'd say I'm handing over to Daniel here, who did the main coding work.
So, okay, first of all, how do we get to our protocol definitions? A good start is to sniff the packets from a protocol transaction and look at the spoken package and try to transform a protocol definition out of this. Mainly you get a Wireshark sniff of your protocol and kind of rebuild the protocol structure in your Spike script. That sounds easy, but you need some understanding of the Spike internals to know what you have to do, and even it's not that easy to get the protocol to spoke with your device or something, so you will have some work to do. Okay, as an example, we got an ARP script here. This is quite simple. You have in the top some binary values that say something like, okay, we are speaking ARP over Ethernet and stuff. And on the bottom, you see our fuzzing strings, which are the source MAC, destination MAC, and the associated IP address. But here comes up our first problem with Spike on layer 2. Spike got a branch of fuzzing strings, which it will insert in such an S-string variable. And Spike just insert the string and doesn't look for the size of the variable. But on layer 2 you got strict protocol definitions. This field have to be 8 bytes. And if you're over it, your whole protocol got fixed up. So we have to do some work. We'll have to do a new Spike function called S-string variable sized, which will fix this behavior and cut off the fuzzing string if it gets too long. Okay. Spike is mostly string and integer based fuzz. So, as mentioned before, we had to add the S-string variable size to get cut off the fuzz strings to be in the protocol definition. And the next big problem with Spike was Spike is byte orientated. So you only can write whole bytes on the cable. You can't do something like fill up bit fields or fill up odd length from some variables. So in most TLV cases you got something like a 3-bit field, or you got some flags to set, and it doesn't fit in a byte. So it was really hard to define some protocol definitions if you got these cases. And this is one of the reasons why we later changed on or switched to Sully. Another thing is in Spike, you can't say Spike, okay, I got a field here and this field only got 3 valid cases, and this is case 1, case 2, case 3, please only fuzz this 3. So it's not possible. We tried to add a new function called S-binary selection which does this work, but due to Spike didn't get the best parser for its scripts, it is not possible to run this function out of the SPK script. Only if you write an own Spike binary, you can use it. Okay. Some more additional features we implemented to Spike. We write a new Spike generic sender, which uses SPK scripts for protocol definitions, and we write both for Ethernet 2 and IEEE 802.3 with both a fixed source MAC and random source MAC. We'll come on to later why we implemented that features. So some other features is as random fuzz function, which did nothing else than filled a defined range with totally random. To be reproducible, we implemented an own random function which is based on a known postfix rand, but so we didn't mess up with the common library rand function. Okay, and there are some other functions we implemented. One is called S-binary type and block size LLDP, which is especially for the first 2 TLV fields of the LLDP TLV protocols, and we'll see it later too. Then we got an internal Spike function called L2 write data, which does nothing else than write and given data onto the cable. We tried to implement the S-binary selection, which didn't work out of the scripts, but if you write your own, you can fuzz protocols if you write in binary for it, but it's a lot of more work, so don't use it. Okay. Last function, as string variable sized, as I told, it just cut off the fuzz strings to be in a protocol range. Okay, this is a little overview over the Spike source and header files and how they are interacting with each other, and it's
by the way, we added some documentation. Spike was not too well documented so far. We added a bit of description, which module does what and how is it called from other modules, and all that is in the source tarball that we'll release after this talk.
Okay.
Let's get a bit more practical then. These are the protocol definitions that we have so far. Let's start with a very simple one, MPLS. MPLS in itself is not a protocol, but it's a common term for some technologies, but the most basic part of MPLS is there is an additional 32-bit header which is inserted between layer 2 and layer 3. For us, that means on Ethernet, even though MPLS can be spoken on most layer 2 topologies. Obviously, I mean, in the most basic case, it's 32 bits, and fuzzing of those 32 bits was quite easy, as I will show in the next slide. There is some internal logic how those 32 bits are used. So far, we did not mimic that logic within a Spike script. We just fuzz those 32 bits. And we have a test bed. I have done some research on the MPLS in the last years. So we have a test bed consisting of Cisco 7200 routers running service provider images. They cope pretty well with this stuff, which might not be too surprising, as I mean, MPLS is not really new, and it's only 32 bits. That shouldn't be too much of a problem for a parser. This is how the MPLS header looks like, just to give you an idea. There's a label, and there are 3 other fields who have different functions, but again, what we did was only fuzzing the whole 32 bits, and through them we implemented a working MPLS bed and just injected the packets without too much of a result. But just to give you an idea how packets look like and how the stuff is called, we can show that with 2 simple lines. That was all of the script what you saw there. It's not normal lines.
So
one has to, yeah.
Okay, well, we got a little demo. So this script, just export an environment and call our generic sender. And as you see, packets are generated and they're on the wire. And
here are valid MPLS headers. In some packets it's only 1, in some packets it's up to 4. There's something called label stacking. Here it's several. But this is just to give you an idea that with a 2-line definition, it's possible to generate valid packets, which are, at least for Wireshark and for the devices we tested it with, perfectly valid packets again. Could you please show the command line again to give an idea what's included? What we added is a generic send layer 2. Kind of within the Spike framework, a new program which gets some parameters. This 8847 is Ether type for MPLS within Ethernet networks, and obviously MAC addresses. This is the way how it is involved once you have installed it. So quite easy to use, at least from our perspective. I'll take over again. We have some more demos. This one wasn't too spectacular. Just to give you an idea how the stuff is involved and how the definition looks like. The next candidate we had a look at was LLDP. LLDP is Logical Link Discovery Protocol, an IEEE standardized protocol which takes over functions that before had Cisco CDP and there's XDP. Some of you might know those protocols for devices to discover each other on layer 2 links. I'll leave that to you to explain a bit. LLDP, du kannst übrigens auch ja den Laserpointer benutzen.
Okay. So LLDP itself is a pretty complex protocol. It's built up of TLVs, type length value structures. It got an Ethernet header type of 88CC and send its packet to a special Cisco multicast address. The biggest problem with LLDP was that it got an odd TLV border. So you got 7-bit of size and 9-bit of type. 7-bit of type and 9-bit of size, sorry. And so it wasn't easy with Spike to fuzz these two variables, because the size always have to fit. If the size doesn't fit, the packet is dropped. So we have to add a new function called sBinaryType and block size, LLDP, which gains 2 arguments, the block which we need the size of and the type we want to write into the packet. Then internally we do some dirty shifting stuff to get the 1 byte, the 1 bit in the other byte, and then write it on the wire. Okay. Another problem with LLDP was your device got a kind of internal database. If it got a 1 packet from a source MAC address, it stores the included information, and if another packet from the same source address arrives with other information, it is discarded. So we implemented the random source MAC just to get around this feature. So we rewrite our generic sender L2 and add this option. Okay, this is how the LLDP TLV format looks like. You see in front we got the 7-bit type and the 9-bit length, which doesn't fit in byte border. Okay, just to give you an overview how complex the protocol is, we got very much TLVs, which different types and different information, which we have all to describe in our SPK script to fuzz the whole script. Yeah.
How did you discover that it was ignoring those packets that were the same source?
We tested it against Cisco devices and turn on the debug output and get the message that it has an other information from the same MAC address and will discard the packet. Okay.
Before we switch over to the next slide then, those of you who have some experience with fuzzing, whenever you hear the word TLV, there might be bells ringing. Oh, TLVs, that might be fun to fuzz TLVs. It turns out that the results were quite different as with MPLS. We have a demo again.
Okay.
Hopefully it works. We need a network access, but for the case it doesn't work, we have included the slides with the output, kind of. We'll have a look if network access is available.
Okay. This is a Cisco.
Can everybody see this, or it's a type too small?
Too small.
Okay. Better now?
Raise the bottom bar
Better?
up towards the middle of the screen.
Sorry?
Bring the bottom of the window up towards the middle of the screen.
Okay.
You can drag it in the window.
Like this?
Bottom. Lift it to the bottom. There you go.
Okay. Yeah, you're right. Okay, what do you see here is obviously a Cisco device, and just to give you an idea, on Cisco devices there's a directory crash info on some devices. This directory is empty at the moment. It won't be in some seconds. Hopefully, if the demo works.
Okay.
Okay, once again, one command line, throw some packets. Oops. Okay, that's about live demos. That's the fun part. Okay, so packets are generated. Let's have a look what might have happened. The device does not respond anymore. That's always, I like this when live demos work. So always a good feeling. But I mean, it might be a network problem or something. We'll have a look on this later. We have to wait till it reboots now. Most probably it does a reboot. I'll get back to the slides and we'll have a look. I'll show you on the slides what is visible afterwards. And please keep an eye on it, and once it's responsive again, we'll get back to this. Okay, here we go. This is LLDP, as said, is a pretty complex protocol, which means Simon, there was the team who did this. I led the team, but most of the work was done by Daniel and another guy. And Simon had the duty to get the specification and to transform the specification into a script. He spent quite some time with this. This is only a small excerpt, but once this is available, everybody can use it. That's why we are here today. When from the packets, this is debug output from the router. What is interesting here is several aspects. It was done at 2 a.m. That's a time when the students work. But one can see packets are received by the device, and here comes one of the fuzz strings of Spike. A neighbor is discovered, which is one of the fuzzing strings of Spike. Here you see the Windows background, or the Windows intention. Here's another one which comes in here, like .1/localstart.asp with some encoding stuff. But I mean, those are the predefined fuzzing strings that Spike provides. But the effect, I mean, you could see they obviously had some effect. This effect, is it back responsive?
Yeah.
Okay, we showed it live then. What's in that? There is some way to get an idea what happened. Remember the crash info directory. There should be hopefully there's something within it. like a core dump, or at least some information. It's not exactly a core dump, but it's some basic information about the register state when a crash occurs. Let's have a look at that file. Okay, here we go. We won't cover it in too much detail. What is interesting here? We lost some. I think we lost some lines. Yes, have a look at this. This is C3560. So not really a small device. It's not one of the big ones, but at least it's one in the middle range, which costs a few bucks, and it's running 12 to 40, which is pretty new. Currently, we are at 12 to 44. This is from August. Last year it was compiled. So pretty new image. Medium to high level device running advanced code and still susceptible to a one line. I mean a script which is a bit longer, but one command line and device crashes. By the way, the Shmoo network uses 3562. But LLDP is disabled by default, and I had my hands within the configuration, so at least to my best knowledge, it has not been enabled. Hopefully it hasn't. Okay, back. Thanks, Daniel, for that. Back to the presentation. Here again, just in case the demo hasn't worked, we included the information here again. Next candidate was VTP, a Cisco proprietary protocol, that's virtual trunking protocol, which works in some special way. Here you see the most basic parts of VTP. There are three types of VTP. Three types of messages. There are so-called summary advertisements, sublet advertisements, and advertisement requests. I'll shortly describe the role of those. I mean, this information can be gathered just by reading some Cisco documentation, so it's not too important for this talk. VTP mainly is responsible for maintaining a consistent VLAN database between devices. So if you add one VLAN on a device, say number 5, and give it a name, say Shmoocon, this information is propagated to other devices. Hey, neighboring switches, listen, there is a new VLAN number 5, which has the name Shmoocon. VTP itself is susceptible to quite some attacks, which are implemented within Yersinia. Once you can have access to VTP, one usually can erase the whole VLAN database, which brings the whole network down, but this is not what we cover here. So VTP, we built for two of those. I mean, you see there's a quite, here are no TLVs in the summary advertisements. No dynamic structures here. In the sublet advertisements, which contain the actual VLAN information, there is some dynamic fields, at least several VLAN information parts can be included. And those are the two spike scripts we wrote. Unfortunately, we tested with quite some switches, and it turned out, even though the packets seemed valid, at least for Wireshark and at least from debug output, nothing happened, which was a bit, on one side, disappointing. On the other side, I mean, you can't expect everything to work or everything to work in a way that causes havoc. And I mean, given we are networking guys, this gave us some, let's say, confidence. At least this protocol, which is enabled by default on all Cisco switches, there seemed no problems, but at least we asked ourselves why. Is there any reason why we don't see anything happening on the devices? And in fact, there is a reason. In September 2006, Cisco issued a major advisory as for Cisco wheel and trunking protocol vulnerabilities. They did a complete rewrite of the VTP code in advance of this advisory after several researchers, most notably FX from Germany, had discovered weaknesses. And after Yersinia came out in March 2005, the Yersinia VTP implementation caused lots of devices to crash. Independently of that, FX discovered vulnerabilities, and they did a complete rewrite, so obviously they fixed a lot of problems. But there is another candidate in Cisco space, strongly related to VTP, that's DTP.
Okay. Base problem with DTP is there is no Cisco documentation public available. So we had no good starting point to build up our scripts for Spike, but there is a Wireshark parser. So this parser saved us a lot of work. We just looked at the C files from Wireshark and nearly got a whole protocol definition. We only have to transform it into our Spike script. We could have looked into the Yersinia code too to get a protocol definition, but it worked with the Wireshark code. Okay, DTP is the same as VTP, encapsulated in an IEEE 802.3 packet, and it got the subnet access protocol header type with 2004. Doesn't matter, only for the Spike command line. So it's based up on TLV, and this TLV's yeah, this TLV's got a 2-byte type, 1-byte length, and the data. So there are 4 known type of TLVs, which is the DTP domain. You can configure that domain on the script. It says something like, okay, you're in my domain, I will trunk with you, or you're not in my domain, I will not trunk with you. Something like that. It contains an status TLV, type TLV, and a neighbor, which just holds the MAC of the other script, other switch. Sorry. Okay, we need to make some changes to Spike to get this protocol fast. We had to implement the use of an IEEE 802.3 header. All the time we only use Ethernet 2, but that wasn't that hard, because libnet, the Ethernet lib we used, just could do it. Just had to do to implement and switch and say, okay, we want to use that one or that one. The other thing is we modified Spike to not only fuzz the integer borders, except to fuzz the whole integer range or the whole word range to get all possible combinations generated. And of course we have to create a script, which wasn't that hard because we got a Wireshark protocol definition and only have to transform it. Okay, that's the script. We have the header on the top and the 4 different TLV types. Not that hard. And what happened? We tested again the same testbed than VTP, and we got some strange things happen. Okay, we sent packet on one switch port, and the trunk on other switch ports goes down, goes up again, goes down, and Okay, some other ports change into old blocking, which means no packets transferred on these ports, and it looks really funny. The device blinks like a Christmas tree. Okay.
Do you guys do any testing on PRP or HSRP?
Not yet.
Are you planning to? Yeah.
Depends on time and cycles.
Have they done any testing of structure definition with PRP or
So far, we have only those 5 we mentioned, and ARP, which was to get an understanding of the structure. But ARP is not, in the strict sense, it is not even layer 2 protocol. Only those 5 grids we have so far.
Okay, this is part of the debug output from the device, and as you can see down there, VLANs are removed.
Note the time of the day when this was done. Okay.
Okay, and down on the last line, you see on port fast Ethernet O/2, our packets came on fast Ethernet O/1, and we sent packets on port 1, and port 2 changed state into blocking.
Have you tried any differences when you had things like port fast turned on versus not?
No, we didn't. I mean, it's not SDP. It shouldn't have any effect if port fast is on or not. It's DTP, which is, again, enabled by default on all ports on Cisco switches.
Okay.
As for the Christmas tree,
Want to see the switch?
this is the
We get
should be.
packets still coming in on this port, even if the LED is off.
That was quite funny to see this. It's a lab device, so there's no productive entities, but still, you see. Nice, isn't it?
Okay.
Okay, so far for the Christmas tree. Okay, next. It's your part.
Okay.
Your part.
Did you try to anything bigger, like a multi-blade switch, just to see what
Yeah, I mean, we tried. As you might have noticed in our test bed, we have some 2900s, 3500s, some 3750s, and a 6509. The 6509 was quite resistant. But I mean that for us it was more about gaining protocol understanding and having fun generating packets. We have not yet conducted very strict formalized test cases.
I was just wondering how the Christmas tree looks on us. Way more blinky.
Yeah, the Christmas tree might have been a bit more animated than.
So, okay. After we got the first success, we had a break in our development, and when we get back to development, we decided to switch to another fuzzing framework called Sully, which was
released last year in summer. Some of you might know. I think there was a talk at Black Hat about Sully, and there's a book about fuzzing from the authors of Sully. So this is the new kid on the block, kind of.
It got some cool new stuff, like it can use the same syntax as in Spike scripts. You don't have to rename your functions, you don't have to rewrite all the protocol definitions, but you don't get that crappy Spike parser. If you write an SPK script and want to write an commentary on one line, the whole script didn't get parsed, and stuff like this. Okay, so you got real Python instead. Python is really cool. And the other thing, which is really useful for layer 2 fuzzing, is you got no byte limitation, as you got in so-called S-bit field, which Sully uses internal to fuzz all integers, to fuzz all strings, and it's really useful. Okay, it wasn't that hard to implement the layer 2 stuff in Sully. Patch only got about a few hundred lines of code, and by the way, we found and fixed a bug in the S-bit field function. Was only one parameter lost on the way down Sully, and we added a new function, or we added a new flag to the size function, because that was the only function that was limited to bytes, and so we added a flag to don't use the length at bytes but at bits. And so we started porting our Spike scripts to Sully, which isn't that hard. You just have to adjust the syntax from Spike to Python, like removing all the semicolons, and add some session handling for Sully, as you have to define the target. You didn't define the target on the command line as in the Python script. Okay, the first protocol we brought to Sully was ARP. Was very, very easy. The second one was DTP, but with Sully we didn't see the same results as with Spike. So why we didn't see them? Because Sully got a whole of the Spike fuzzing scripts reused, but not all, and we didn't fuzz the whole range. We just want to port the protocol to the Sully framework and try to test our layer 2 ability. Okay, that's the Sully ARP script. The part in the middle looks the same as in Spike, and then you have real Python. You have to import a module and do the layer 2 header, the Ethernet header, not on the command line but in the script, and on the bottom you see some session handling stuff. Okay.
Okay, then the first and so far only protocol that we implemented only in Sully is another Cisco proprietary protocol called WLCCP, which is mainly responsible for inter-AP communications in some Cisco wireless setups. Mainly, I mean, the protocol is, from our understanding, is flawed anyway, architecture-wise. It's responsible for APs can elect some kind of master, and this master caches authentication information to have a faster roaming process once the user has a handover from one cell to another cell, or from one AP to another one. So a quite exotic protocol. Again, like with DTP, absolutely no documentation available. Wireshark gave a starting point, but from our impression, let's put it like this, we think the Wireshark implementation is not very mature. And when sniffing WLCCP packets with Wireshark, there are lots of invalid or unknown TLVs within the output. So we had to try to rewrite the whole definition from our from just sniffed packets. WLCCP is quite complex. Again, this is only an excerpt of the script. Most interesting from your perspective might be the results. So far, we have not too reliable or not too many results. We think it's because WLCCP, we have not yet understood the inner workings to some degree. requires some kind of state. So one packet is an answer to another one, and has to act accordingly. However, now and then APs crash and have to be hard to reset that, but we are not able to reproduce it in a controlled manner. So start a script, and then we have a given amount of time, let's say 30 seconds or something, and APs crash. But usually it's like several APs within one given layer 2 domain. We start throwing packets in, and after some time, some AP, it's not predictable which one, dies. So there might be some problems, but we can't identify them further at the very moment, which means next steps could be gain more understanding of the protocol by reverse engineering it, or at least more understanding it better from the network behavior, and understand the state machine, so one might be able to adopt the scripts here. Okay, so this one was the last protocol, not the most spectacular one as for the results, but at least the demo worked and we had a Christmas tree. The code of all the stuff is available. You can download it from our website. There is a tar file for the whole spike, and there's another tar file which contains a diff file for Sully and the protocol definitions. From our understanding, these are stress testing tools, so the German so-called hacker paragraph shouldn't jump in. I mean, we are pretty relaxed as for the paragraph anyway. Given enough time and cycles and young students coming into ERNW, we will continue the work. Feel free to contribute in what way. If you have cycles left and you think some protocol could be interesting, get the stuff, try to understand it, and it's not too difficult to write the definition scripts once you understand the format of a protocol. Talking about code, there's another thing that's new that we put on the website. From a talk we gave 2 years ago, that we released the tool as an apathetic Perl script, which was updated in the course of a project, so this one is available too there. Which brings us to the summary. We had some fun with Spike. We expect more fun with Sully. Our goals were to learn about fuzzing and frameworks and protocols, and these goals I can certainly say were fulfilled. We learned a lot. In the meantime, we use a lot of fuzzing, and when doing custom application testing, so we profit from that knowledge. I mean, by the way, it turns out that some big vendor has parser problems, but that was not the thing we were concentrating on. Yeah, that's all. Have a good party then. Are there any questions? Yes.
I have two questions. On the beginning slide, when you had commercial solutions, you had a subset of evolutionary fuzzing. Can you talk a bit about that? Is that really like genetic programming, where you have where the strings start merging?
No, that the evolutionary framework of component within GPF is you can kind of connect. You have a fuzzer bringing some stuff in, and you can connect that to some, let's say, debug interface, which monitors the behavior on the fuzz destination. That's what they call evolutionary.
And that, I found that actually interesting, that error that you got in translation, look aside buffer cache missing, that caused crash. Do you have an explanation for that?
Well, we have not yet asked for one. But I mean, again, it was for gaining some basic knowledge on these techniques, not on understanding what happens then. I mean, we were a bit surprised to see how easy it seems to cause havoc on devices, but given that vulnerability research was not the main intent, we did not even open a disclosure process for this. So Cisco might be a bit upset, but yeah. Luis.
For fault isolation, do you do anything to help fault isolation?
Not yet. No.
You just throw a
Yeah.
bunch of packets and solve it.
Yeah. We did not have to. I mean, we have. Once we had cycles left, it was okay. Do we do structured test cases, or do we spend the time for new protocol definitions? And we chose the latter.
And why didn't you use STP? Why didn't you try?
I mean, STP, as well known, deployed since 20 years. One could expect parsers are good there, I mean, as I said, it was about getting knowledge of some exotic protocols. STP is not too exotic. Any more questions?
Do you know where the knowledge of protocols came from for the Layer2 protocol decoders that you were able to find? I mean, did somebody, was it just trial and error, or were
No, we don't know. I imagine, I never paid attention to, I imagine there must be some repository. You must be able to get the information, but we did not. I have a question down the back.
Did you find that the devices were quite sensitive to how fast you sent your packets?
Depended on the protocol. With LLDP, yes, very fast kind of response. With VTP, the DTP depends. What we could, in most cases, we could observe that response times went up significantly, which means, I mean, one could say, okay, it's packet coming in, but those devices are intended to handle much more load than this fuzzing cost, which gave us usually, when response time went up, for us this was an indication, okay, the state machine, some parser has work to do, and some state has to be kept and stuff, which once this happened, we got more confidence, okay, there is something not like it should be. If there are no more questions, thanks for your attention. And have a good party, everybody.
You know the guy who asked the last question who he is, right? You know the guy who asked the last question?
No.
You know who he is?
No.
His name right now. He wrote Spike. Who's the guy who wrote Spike?
Ah, okay. Thanks for that. The one, he...
Yeah. Dave.
I just thought that you already offer hi.
That was awesome, dude.
Thanks for your work.